In 1774, in a small laboratory, an English minister set up quite a peculiar scene. A lump of strange red powder was sealed in a glass, suspended in a pool of liquid mercury, and placed under a giant lens aimed to catch the sun. When the sunlight hit, the red powder began to mysteriously vanish. Beads of a silver-colored metal appeared on the glass, and an invisible gas slowly began to fill the space above. That gas turned out to be so powerful that, as the minister noted in future experiments, candles roared with a vigorous flame, and mice could breathe 4 times longer than they could in ordinary air. The minister tried to explain it using an old idea known as the theory of phlogiston. Phlogiston was a supposed invisible fire substance that things were thought to give off when they burned. Air acted as a medium for burning and absorbed phlogiston when materials such as candles burned. Since the gas that the English minister observed burned so brightly, he called his discovery dephlogisticated air and moved on. What he didn't know, though, was that far to the north, a quiet German-Swedish apothecary was isolating the same mysterious gas and concluding very similar things about it. And meanwhile, in Paris, a young aristocrat and chemist was observing burning metals, but from his results was instead wondering if the entire theory of phlogiston was backwards. This is the story of how 3 men from 3 different countries slowly realized over the course of a decade that air isn't just air, and how that realization killed an invisible theory of fire that ruled chemistry for almost a century. To understand why that red powder experiment was so confusing, we first have to step into the chemistry of the early 1700s, when almost everyone believed in the dominant theory of phlogiston. The idea was simple and alluring. Anything that burns contains a kind of fire substance. So, when wood, oil, or another material burns, it doesn't combine with anything. Rather, it's losing this invisible phlogiston, which is being absorbed into the air and leaving behind a dephlogisticated residue like ash or rust. German chemist and physician Georg Ernst Stahl turned this into the dominant theory of the 18th century. All metals were loaded with phlogiston. When they were heated in air and turned into a powdery calx, chemists said the phlogiston had escaped. And when you heated that calx with charcoal to get the metal back, you were just pumping phlogiston into it again. For a while, it worked disturbingly, well, giving one unified theory that extended beyond that of flames. It worked well with rusting, smelting, and even for breathing, where living creatures were thought to slowly give off phlogiston to the surrounding air like a very slow fire. But, as it goes with all outdated theories, there was a fundamental problem lurking in the balance. By the 1770s, chemistry had become much more quantitative and much more oriented towards weighing every reactant and product. The more precise the balances became, the harder it was to ignore that something from the air was sneaking into metals and making them gain mass. The burning question would continue to present itself more and more throughout this decade. And as the 3 men I mentioned before performed their experiments, the theory of phlogiston would start to crack under the enormous amounts of mounting evidence against it. In Uppsala, Sweden, between the years of 1770 and 1774, a young apothecary named Carl Wilhelm Scheele was wrestling with an interesting puzzle. A professor friend of his had complained that his saltpeter, when heated and then treated with acid, gave off strange red fumes. This experiment had seemingly provided evidence that there were still unknown airs, the ones that were released as fumes, hiding inside familiar substances, even substances chemists thought they understood relatively well. For Scheele, who spent his days preparing medicines in a provincial pharmacy, this was an invitation into the forefront of chemistry. Saltpeter was understood as a building block of chemistry at the time and was thought to be constructed out of 2 components. The first was potassium, which at the time was known as vegetable alkali, and the second was called spirit of nitre, a highly corrosive liquid acid that had been extracted from saltpeter many times before. If seemingly familiar materials like saltpeter were suddenly releasing air under heat in specific conditions, then for Scheele, the only way to understand what was happening was to heat everything he could get his hands on and see what came out. And so, Scheele began a systematic siege on matter. In his cramped lab, he heated manganese dioxide, mercuric oxide, silver carbonate, chalk, and various nitrates in small glass retorts, connected to bladders or inverted jars, so that any gas released would be trapped rather than lost to the room. Each time a solid gave off a gas, he collected it, tested how it smelled, whether it extinguished or fed a flame, whether it killed or sustained small animals, and also how it reacted with lime water or alkaline solutions. From some materials, he obtained foul air that put out candles and suffocated mice. From others, he got gases that turned lime water milky or smelled pungent. But from a particular group of substances, heated nitrates and metal calxes, he repeatedly drew out an invisible substance with a very peculiar behavior. This gas had no obvious smell or taste, yet in it, candles burned with an unusually bright, almost dazzling flame, and glowing coals suddenly flared up the moment they were introduced. Under a flask filled with this new gas, the candle blazed so fiercely that the flame rapidly consumed the entire volume. Small animals placed in the presence of this gas seemed to breathe more easily at first, and he also noticed that this gas restored the burning power of air that had been partially exhausted by flames. From these experiments, Scheele concluded that common air was not a simple element, but rather a mixture. Roughly 1/4 of this active gas, which he named fire air, and about 3/4 of inert air that did not support combustion or life. Interpreting everything through the lens of Phlogiston theory, he imagined that substances rich in phlogiston combined with fire air when they burned, producing flames and heat and leaving behind calxes once the phlogiston had been fully driven off. By the early 1770s, working in his quiet, methodical way, Scheele had effectively isolated the gas we now call oxygen from multiple sources. He wrote up his findings in a manuscript on air and fire, and even drafted a letter to a rising French chemist named Antoine Lavoisier. Unfortunately, however, Scheele's manuscript sat in the hands of a publisher and did not appear in print until 1777, 5 years after his key experiments. As a result, Scheele's priority remained largely invisible to his contemporaries. While Scheele was filling bladders with fire air in Sweden, an English chemist by the name of Joseph Priestley was attacking the problem of air from a very different angle. As a dissenting minister and amateur experimenter, he was fascinated by what happened to air when things burned or animals breathed in it, and also by the strange fact that green plants seemed to repair whatever candles and animals did to air. In his famous bell jar experiments, Priestley concluded that both burning and breathing seemed to injure the air, but plants somehow restored it. By the early 1770s, he began heating substances like the red calx of mercury. On the 1st of August, 1774, Priestley focused sunlight through a large glass lens onto a sample of this red powder sealed in a vessel over mercury. As the red solid decomposed, silvery droplets of liquid mercury appeared, and a colorless gas accumulated above. A candle lowered into it burned with an intensely bright, vigorous flame. When he confined a mouse in the gas, it lived roughly twice as long as it would in common air. Priestley inhaled the gas himself and noted that it felt incredibly pure. However, when it came time to name and interpret the gas, Priestley stayed loyal to phlogiston. He named the gas dephlogisticated air and published his results in 1775, helping to cement his reputation as the discoverer of this remarkable substance. In the autumn of 1774, he traveled to Paris and described his red calx experiment to the French chemist Antoine Lavoisier. In doing so, Priestley effectively handed him the crucial clue needed to tear down phlogiston. Years before he ever heard of Priestley's work, Lavoisier had begun heating metals in closed vessels and tracking every ounce that went in and out. His results were astounding. The metal had gained weight, but the total mass of the metal plus trapped air had stayed the same. From this, he concluded that some portion of the air had combined with the metal to form the calx. When Priestley described his red calx of mercury experiment, Lavoisier immediately recognized an opportunity. He obtained the red powder, heated it in a carefully weighed apparatus, and showed that the mass of the original calx was exactly equal to the mass of the regenerated mercury plus the mass of the liberated pure air. The gas that exuded from this powder supported combustion and respiration, just as Priestley had described. But Lavoisier interpreted it not as dephlogisticated air, but as a distinct, previously unrecognized constituent of the atmosphere. Because this new substance seemed to show up in products of burning materials that formed acids, Lavoisier proposed that this gas was the universal acidifying principle and coined a new name for it: oxygen, from Greek roots meaning acid former. In his 1789 publication, Elementary Treatise on Chemistry, he built a whole new chemical language around oxygen, replacing the old talk of phlogiston with terms and formulas that reflected mass, balance, and definite composition. By treating Scheele's and Priestley's mysterious gas as a real element that combined with matter during combustion, Lavoisier was able to show why metals gained weight when they burned. Even after Lavoisier laid out his oxygen theory, not everyone was ready to abandon phlogiston. Priestley himself became one of the most vocal opponents of the French system, stubbornly clinging to the old theory until his death. What finally broke the stalemate wasn't rhetoric, but rather measurements. Throughout the 1780s and 1790s, increasingly careful quantitative experiments proved the theory of phlogiston absolutely incorrect. Lavoisier's insistence on the conservation of mass made it far easier to predict and organize new results. In the end, Scheele and Priestley had both held oxygen in their hands first, but tried to explain it with an incorrect theory. Lavoisier's bold move was to put air itself into the cast as a reacting substance and to trust the balance over intuition. That is why today, the same gas that Priestley called dephlogisticated air and Scheele called fire air is known simply as oxygen, marking the moment when chemistry turned into a quantitative science.